Question 7. An electron moves into a uniform magnetic field as shown. Uniform means it's all the same, equally spaced out lines. And we have to state the direction of the force experienced by the electron as it initially enters the magnetic field. Now, as you can see, the magnetic field is pointing into the screen. That's what the symbol cross means. If it was pointing out of the screen, it would be a dot. The electron is moving from left to right. Now, to find out where the electron will be forced, we have to use this famous hand equation called Fleming's right hand rule for negative charges. You use your right hand, and your first finger is the direction of the field, which means it'll be pointing straight into that screen. Your second finger will not be pointing as shown in the picture from right to left, but it'll be pointing from left to right in this direction, and that means that your thumb's going to have to spin round and point downwards, so that electron is going to move downwards. Now we can watch this little simulation and you can practice your right hand rule for negative charges. Remember, if it becomes a positive charge, you must use the left hand rule. An easy way to remember that is the famous statement by the management who put on the Elvis Presley shows, and they would say, Elvis has left the building, and someone would say, are you positive he's left the building? So for positive charges, you use your left hand. Let's have a look at the simulation and see what we get. And here's the simulation here. We have the magnetic field pointing into the screen, and we're going to fire an electron, which is a negative charge, and see where it goes. And it's going to be forced downwards. If we had to reverse the magnetic screen out the way like this, then the electron is going to go up the way. It's going to go the opposite direction. We can change the charge to a positive charge, and you have to use your left hand rule for this. So try out your left hand rule. We fire the left hand rule in, then for a charge which is going to be positive, when the magnetic field is into the screen, it's going to move upwards. If the magnetic field is out the screen, the charge is going to move downwards. Now our question was the negative charge moving in like that to the screen. The magnetic field was inside and pointing into the screen, and you can see it's going to go down the way. So you have to practice your right hand rule to get that. First finger of your right hand, because it's a negative charge, point it into the screen. Twist your second finger round until it's going from the left position to right position, and your thumb should point downwards. Got it. Now if the field is out of the page, it's a little bit harder to do. You have to point towards yourself, and your finger will be moving from left to right again, and your thumb should be moving up, your thumb should be up the way. Therefore the negative charge is moving up the way. And you can practice with the positive charge as well. Positive charge into the screen, you have to use the left hand rule for that, because positive is left the building. Use the left hand rule. And there's a positive charge with the magnetic field out the screen. It goes down like that. So you have to play about with these diagrams and make sure you know your left hand and your right hand rule. Here's a diagram showing you two speakers connected to the same signal generator. That means that the sound coming from speaker 1 and the sound coming from speaker 2 are coherent, and you should be able to hear an interference pattern along this line here if you walk back and forth. Now we're told the position P, the central maximum, exactly halfway between the two speakers, we're told that we hear a maximum sound. The next maximum sound occurs at position Q. Now, we're given the path difference to Q. That's like taking a ruler and measuring the distance from speaker 1 to Q and from speaker 2 to Q. And the two distances or two lengths are shown on the diagram. Now, what is the condition for the first maximum sound to be heard after the central maximum? And this can be remembered by using the following chart. We know that the first maximum sound after the central maximum tells us that the path difference between the two speakers is one whole wavelength. If we heard the second maximum sound after the central one, the path difference between the two speakers would be 2 lambda. And if we heard the third maximum sound after the central maximum, the path difference between the two speakers would be 3 lambda. Now in this case we're told we hear the first maximum sound at position Q. So what is the condition for the first maximum sound at position Q? And the condition is that the path difference between speakers 1 and speaker 2 will be exactly equal to one wavelength. One complete wavelength. So what is the path difference? Well, the path difference is easily found. It's speaker 1, 1.7 meters. Take away 0.8 meters. And that gives you the path difference. And if we work that out, we get the path difference is going to be 0.9 meters. So the wavelength of the sound, lambda, must be equal to 0.9 meters. Now likewise, what would be the path difference to the second maximum sound? Well, the path difference to the second maximum sound would be double the wavelength, which would be 1.8 meters. What would be the path difference to the third maximum sound if we heard that from P? Well, once again, the path difference would be 3 whole wavelengths. So that would be 3 times this wavelength here, which would be 2.7 meters. So this is the chart you must remember. The central maximum sound, there is no path difference. The first maximum sound, the path difference is 1 whole wavelength between the speakers. The second maximum sound you hear, the path difference would be 2 wavelengths. And the third maximum sound, the path difference would be 3 wavelengths.